Welcome to the network lecture series. Myself, Dr. G. S. Sadish Kumar, Assistant Professor, Erode Singh Engineering College, Tamil Nadu. Today we are going to discuss about the resonance. So, what is resonance and all? So, topics to be covered in this lecture series are resonant definition. What is the resonant effect and analysis of series resonant circuits and analysis of series or LC resonant circuit, and very important thing, what is the application of the resonant circuit. So what is the resonance and what is the resonance effect? So inductive reactance increases as the frequency is increased, but capacitive reactance decreases with higher frequency. So because of these two opposite characteristics, for any L and C, that means inductor and capacitor combinations, there must be a frequency at which the XL equals the XC. Once increases while the other decreases. So this vice versa, XL and XC. These cases of equal and opposite reactance is called as a resonant. And the AC circuit is then a resonant circuit. Then AC circuit can call it as a resonant circuit. So what and when the circuit will be a resonance, the frequency at which the XL that is equal to XC is the resonance frequency. So at which frequency the XL and the XC both will get equal, that frequency we can call it as a resonant frequency. So the inductive reactance and capacitive reactance are totally depends upon the frequency. So if we are varying the frequency, vice versa, the inductor and capacitor will be varying. But at one particular frequency, the XL value that is equal to XC value, that is called as a resonant frequency at which the XL equal to XC is happen. That is, we can call it as a resonant frequency. At that time, the circuit will be act as a pure resistive circuit. So at the time, the circuit will be purely acting as a resistive circuit. That means the power factor of the circuit at that time, that is unity, right? So what is the applications of the resonance circuit? The mostly main application of the resonance circuit is in tuning circuits. The most common application is for a tuning circuit. That the example for radio frequency. So we have different types of frequency in atmosphere. We need to collect a particular frequency, so we can go for a resonance circuit. So figure shows we have a different types of frequency like 50 kilohertz, 750 kilohertz, 1000 kilohertz, 1250 and 1500 kilohertz. I need to get only the particular frequency, that is 1000 kilohertz frequency. With the help of this LC or LC circuit, I can get the exact frequency by tuning by changing the values of inductor and capacitor. I can get the frequency as expected frequency, that is FR, that is we can call this a resonance frequency 1 divided by 2 pi root of LC, that is frequency. So we can adjust the value of the inductor and capacitor. So inductor and capacitor both are variable, so we can change the value of inductor and capacitor. By changing this, we can get the required frequency as an output. So this is the main application of the resonance circuit. So mostly in a communication, the resonance circuit will play the vital role to get the exact frequency and tuning applications. So we are going to discuss about series resonance. At the resonance frequency, the inductive reactance and capacitive reactance are equal. So we already discussed XL, that is equal to XC at a resonance condition, resonance frequency. In a series AC circuit, the inductive reactance leads by 90 degree. So in a series AC circuit, the inductive reactance leads by 90 degree compared with the zero reference angle of the resistance. So we can, in a reference, we can tell it as a resistance. So it lead, so inductive reactance lead 90 degree and capacitive reactance lags by 90 degree. So we can take it resistance as a reference. So from that resonance, the inductive reactance leads by from that reference 90 degree, for a capacitive reactance lag from that reference by 90 degree. So in that the phase angle between the out of phase between XL and XC are 180 degree out of phase. The opposite reactants cancel each other and complete when they are equal. So once the XL and XL both are in opposite phases, so once this XL value that is equal to XC value, the both are get cancelled and we can get only the value of R. So this is a series resonance circuit. Series resonance circuit. In a series resonance circuit, we have R, L, and C. So we can here we will discuss only L and C. So F equal to the resonance frequency, that is 1 divided by 2 pi root of L C. So FR, that is a resonance frequency in hertz, L that is an inductance value, C the capacitance in farads. Okay. So by changing this L and C, we can get obtain the required resonance frequency. That means we are tuning means we can make it XL that is equal to XC. At one particular level, particular frequency only, this XL will be XC. If the frequencies exist, means this condition will be varied. Condition will be maybe the circuit having a more XL value and less XC value. Likewise, so in a series circuit, if the above frequency, the circuit will be having only capacitance value. If the frequency lower than the if the frequency is lower than the resonance frequency, the circuit value will be behave as an inductor type in a series resonance circuit. So in a series resonance, we have resistance, inductor, capacitors, everything is connected in series here. XL and XC equal, resulting in net resonance of 0 ohm. The only oppositions to current is the coil of resistance RS. Only we have RS current. So here you can see this is the XL, this is XC. We can take it as both. We can 0. We can take it as a reference here. So XL, that is an inductor value, XC capacitor value. These both are 180 degree out of phase. So here the XL equal to 2 pi FL. This is starting from 0. It will gradually increasing, and the Xc equal to 1 by 2 pi Fc. The value is gradually increasing here. So at one frequency, this value XL value, for example, it is a minus 5. Then XL here that will be equal to plus 5. So this is a plus 5 and this is minus 5. So both will get cancelled, and at the time the value will be 0. So that frequency, these both values are same. That is called XL equal to XC at that is resonance frequency. We can call that XL that is equal to XC, that is called F for this resonance frequency. So we can take it as a small example here. You can get a smaller resonance series resonance circuit. What will happen? Resonance rise in VL and VC. So these are two 20 volt 50 kilohertz supplies given. So here are 4 amps XC, that is capacitance 31 ohm, the inductor is 31, both will having the same value. So in this we can find out the current, that is, so IR equal to 20 divided by 4. So 20 divided by resistance value, we can get the 5 amps. This is current. So we need to find out the value of V across the inductor, V across the capacitor. So VL equal to I into XL. We can get 155 volt. And same, this both values are same. So okay, VC equal to 1 into XC, that is equal to 155 volt. Note the reactive voltage are phasor opposite and they can call VXL plus VX. So both values are in opposite direction. Clear? Because in a XL it is in positive, XC it is in negative. So we can see in this previous. So both are in opposite values. Okay. So VL, it is minus 5 150. So VL 155, VC equal to minus 155. So both we are adding, that is equal to 0. Plus and minus, that is equal to 0. So resonance rise in VL and VC. So if the resonance is increasing, so Q equal to 7.8 ohm and Q equal to 35. This is 5 amps. R equal to 4 ohm. This is 1 microfarad and this 1 millihenry. Here, so same way 4. And what will happen if Q equal to 0.7? So VL equal to I into XL. So both the value, this 1 microfarad, this 1 microfarad. Okay, 1 microfarad and 1 millihenry. Right. So VL equal to 1 into XL 155 ohm. VC equal to 1 into XC 150. See here we can just Q, that is a quality factor, that is equal to 7.8. So 7.8 into 20, we can get 155 ohms. So Q into Vs, quality factor into source voltage. We can get the value of same value 150. Q we can call it as an quality factor. So here we can listen quality factor 32. So VL equal to I into XL, same value I into XL 640, then I into XC we can get same value 640. Then quality factor that is here is 32. So 32 into 20 volt we can get the 60 volt. This is quality factor. Q is then quality factor in resonance circuits. So what is frequency response? So what about the frequency response in a series resonance circuit? So in a series circuit, so R4 and C equal to 1 microfarad, L equal to 150 Henry, all contained in series. So we can find out the value of F4, that is resonance frequency, that is equal to 1 divided by 2 pi root of L into C. So what is the value? You can find out the resonance frequency for this circuit, 1 divided by, so inductor 1 into 10 power microfarad, so this one 1 into 10 power millihenry, 1 into 10 power minus 3, and capacitor 1 microfarad, so 1 into 10 power minus 6, we can get 5.03 kilohertz. So this is the, sorry, so this is the resonance frequency. So now we can draw the graph. So this is 0, this is current 5. Okay, so it's a frequency. So at the time the frequency is increasing, is 5.04, the frequency is 5.03 here. So 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 in this we can get the frequency FR, that is equal to 5.03 kilohertz. So 5.03 kilohertz. So in this condition, the XL equal to XC. So in this time the circuit is at equal to R. So in this resonance frequency condition, the circuit having only resistance value. So this is very low resistance in this condition. So the maximum current will be in this circuit. So it will get the maximum current. So I equal to maximum in this condition. I equal to maximum because of XL, that is equal to XC. So both the values are get cancelled. So Z equal to R plus J into XL minus XC, that is an impedance. So XL that is equal to XC, both are get cancelled and 0. So Z equal to only R. So at the time the resistance of the circuit is very very low. So the resistance is very low. So the current in the circuit is maximum. So that's why in this condition the current will be very low. After that the frequency is increasing. The inductor value and capacitor value both are get cancelled each other. So circuit will having only resistance value. So that resistance value is very minimum in this circuit. So the resistance value is very minimum, we can get the maximum current and the at the resonance frequency. So at the time of resonance the circuit will get more current, and because of the less resistance value. Okay, also the at the resonance condition, current will be maximum and resistance will be a minimum value. So you can go for series RLC circuit, RLC. Here what are the important parameters in this series RLC circuits are: inductive reactance XL, that is equal to 2 pi F into L. So reactance 2 pi FL, you can call it as an omega L. So 2 pi F, that is equal to omega. So XL equal to omega L, we can represent. Then capacitive reactance X equal to 1 by 2 pi Fc, that is equal to 1 by omega C. When XL greater than Xc, that means the inductor value is higher than the capacitor value, the circuit will be a pure inductive circuit. Circuit will be an inductive circuit. When the Xc greater than XL, then the circuit will be an capacitive in nature. So total reactance Xt equal to XL minus Xc or Xc minus XL. That is a total reactance. So what is the total impedance? That is equal to Z root of R square plus X L minus Xc the whole square, or otherwise St the whole square. We can represent as R plus Jx. So Z equal to R plus Jx. That is a total impedance Z in this series circuit, series RLC circuit. For the above equation for inductive reactance, If either the frequency or the inductance is increased, the overall inductive reactance value of the inductor would also increase. If the frequency increase or inductor values increase, of inductor would also increase. As the frequency approaches infinity, the inductor reactance would also increase towards infinite with the circuit element acting like an open circuit. Clear? Yes, the frequency is approaching infinity. The infinite value, what about the inductor reactance? It is directly proportional, it also increases towards the infinite when the circuit elements act like an open circuit. Clear? If frequency is increasing, if the inductor frequency is gradually increasing, if inductor is directly the inductive value is directly proportional to the frequency, if the frequency is continuously increasing, it will frequency approaches to infinite. So it will denotes that the circuit is open circuit. For a capacitor it is really opposite, because of the if the frequency is increasing, the capacitor values totally get reducing, so it will behave as a short circuit. Clear? However, the frequency approaches zero or DC, the inductive reactance would decreases to zero, causing the opposite effect, acting like a short circuit. This means that the inductive reactance is proportional to the frequency and is small at low frequency and high at higher frequency, and this demonstrated in the following curve. Here you can see the frequency and reactance. The graph of the inductive reactance against the frequency is a straight line linear curve. The inductive reactance value of an inductor increases linearly as the frequency across its increase. Therefore, the inductive reactance is positive and is directly proportional to the frequency XL, directly proportional to F. If F is increasing, the XL in a zero, F is increasing, so both are get increasing linearly. So XL equal to 2 pi FL. The same is also true for a capacitive reactance formula above, but it is reverse. Because of inductor and capacitors are vice versa is reverse. If either the frequency or capacitance is increased, the overall capacitive reactance would decreases, right? Because of inversely proportional. As the frequency approaches infinite, the capacitor reactance would reduce to practically zero, causing the circuit element to act like perform perfect conductor of 0 ohm. The capacitor reactance would rapidly increasing up to the infinity, causing it to act like a very large resistance, becoming more like an open circuit condition. This means then the capacitive reactance is inversely proportional to the frequency for any given value of the capacitance. So it is an inversely proportional. The graph of capacitive reactance against the frequency is a hyperbolic curve. The reactance values of a capacitor has a very high value at low frequency, but quickly decreases as the frequency across it increases. Therefore, capacitive reactance is negative and is inversely proportional to the frequency, right? So 1 by Xc. So F is Xc equal to 1 by 2 pi Fc. So Xc is inversely proportional to the frequency. When we can see that the value of these resistance depends upon the frequency of the supply. At a higher frequency, XL is high, and at a lower frequency, XC is high. That is inductive reactance and capacitive reactance. Then there must be a frequency point where the value of XL is the same as the value of XC, and that is if we now place a curve for an inductive reactance on top of the curve for a capacitive reactance so that both curves are on the same axis, the point of intersection will give us the series resonance frequency point. That is, you can see here, if this is an XL capacitive reactance, this is an XL, this is an XC. XC is an hyperbolic curve. XL, that is a linear curve where this XL and XC both are intersecting each other. So that is, we can call it as a resonant condition. So here capacitive and inductive. So if this point we can call this a resonance, so the X is greater. So From 0 to F4, the circuit will behave as a capacitive circuit. From F4 to infinite, the circuit will be behave as an inductive circuit. So F4, that is, you can call it as a resonance frequency. So here the XL minus XC, that is a resonance value. The beating which the frequency the both are get intersected, that is called resonance frequency. So electrical resonance occurs in an AC circuit when the two reactants which are opposite and equal cancel each other out as XL equal to XC. At the point of the graph at which this happened is where the two reactants curve crosses each other. In a series resonance circuit, the resonance frequency F4 point can be calculated as the following. So how we can calculate the resonance frequency? So F4 XL minus XC, then we can know that 2 pi FL, that is equal to 1 by 2 pi FC. From that I need to calculate the value of F. So F squared, that is equal to 1 by 2 pi L into 2 pi C, that is equal to 1 by 4 pi squared into LC. Okay, so need to F equal to root of 1 divided by 4 pi square LC. So F4, that is equal to 1 by 2 pi root of LC, or otherwise it is called as omega R, that is equal to 1 divided by root of LC. So this is the way we can find out the value of resonance frequency in a circuit. Now we can see that then that at resonance the two reactants cancel each other out, thereby making a series LC combination act as a short circuit with the only opposition to current flow in a series resonance circuit being the resonance. Or in complex form, the resonance frequency is the frequency at which the total impedance of a series RLC circuit becomes purely real, that is, no imaginary impedance exists. So, if the circuit is purely real or Z equal to R, the XL equal to XC, at that time the circuit will be behave at the pure resistive circuit. They have only real part, there is a no imaginary part in the circuit. So the total impedance of the series circuit becomes just the value of the resistance, and therefore Z equal to R. That is a resonance condition. Then at the resonance, the impedance of the series circuit is at in minimum value and equal only to the resonance or of the circuit. The circuit impedance at the resonance is called dynamic impedance of the circuit, and depending upon the frequency. XC typically at higher frequency, XC typically a lower frequency will dominate either side of the resonance. In the graph we can see that. Note that when the capacitive reactance dominates the circuit, then impedance curve has an hyperbolic shape to itself. But when the inductive reactance dominate the circuit, the curve is non-symmetrical due to the linear response of the axle. So here we can see this dynamic impedance. That is an impedance ZF, it is a frequency. So it is an intersection curve. So it is an Z equal to R. This is an impedance. At the resonance condition, we both are get cancelled. So circuit having only minimum resistance value, that is Z equal to R. If at resonance frequency, so we can tell, so below resonance frequency in a series circuit, it will act as a capacitor. The above resonance frequency, the series circuit will behave as an inductive in nature. You may also note that if the circuit impedance is at its minimum at resonance, then consequently the circuit impedance must be at its maximum, and one of the characteristics of a series resonance circuit is that admitted is very high. But this can be bad thing because the very low value of resistance at resonance means that the resulting current flowing through the circuit may be dangerously high. So at the XL equal to XC, so circuit having a minimum resistance value, if the resistance value is very minimum, the current will be flowing to the circuit is very high, maybe it is a dangerous value. We recall from the previous tutorial about the series RLC circuit that the voltage across a series combination is a phasor sum of resistance voltage across a resistance, voltage across inductor, and voltage across a capacitor. Then, if at the resonance the two reactants are equal and the cancelling, then the two voltages represent VL and VC must be an opposite and equal in value, thereby cancelling each other out, because with the pure component the phasor voltage drawn plus 90 degree and minus 90 degree. Then in a series resonance, the circuit has VL equal to minus VC, then resulting reactive voltages are zero and all the supply voltages dropped across the resistance. Therefore, VL that is equal to V supply, and it is for this reason the series resonance circuit are known as an voltage resonance circuit because of whatever the voltage supplied by the source that is given to the resistance only. So at the resonance condition, the source will always supply the power to the only the resistance, not for inductor and capacitor. Inductor at resonance condition, inductor and capacitor will interchange the energy. So inductor will transfer this magnetic energy into capacitor, and capacitor transfer this electrostatic energy into the inductor. So the energy will be interchanged between inductor and capacitor at the resonance condition. The source will supply only the power to the resistor. So you can see either side of the resonance, the voltage drop VL minus VC. So the voltage drop equals zero. So here L and C both are get cancelled and it will act as a short circuit. The circuit will be behave as only pure resistance circuit. So this is a condition, series circuit. What is the current condition? So this is circuit current. So I equal to V by R. At the time we can get the maximum current. I this is a R equal to very low. Here I equal to V by ZC and I equal to V by ZL. That is a series resonance condition. So at the resonance condition we can get the maximum current. So phase angle of a series resonance. What is the phase angle between inductor, capacitor, and resistance? So for a capacitor, so it is a source voltage, it is an intercurrent. So it is a lagging for a below FR capacitor. I lead the Vs. So I current will lead the voltage in a capacitor. So for a inductor, for the resistor, induct current and voltage both are in phase. So theta equal to 0 degree. For inductor, the current lag behind the supply voltage. So lag behind the supply voltage Vs. So it an angle of theta. So we can hear 0 Xc greater than XL, it will purely act as a capacitor. Then XL greater than Xc, the circuit having a only pure inductive in nature. So what is the bandwidth? So it is a bandwidth is an it is the difference between a lower cutoff frequency and upper cutoff frequency. That is we can call it as a bandwidth. So it is an I maximum. We can get the maximum current I equal to V by R at one condition where we are obtaining the 0.707 of its maximum value. That is enough. We two times we can obtain the same values. So it is an that is called a first frequency, lower cutoff frequency, and after that some high frequency we can get the same value of 0.7. So the difference between this lower cutoff frequency and this upper cutoff frequency we can call it as a bandwidth. So this is bandwidth. So this is called as an this is a difference between lower cutoff frequency and upper cutoff frequency. We can call it as a bandwidth. So bandwidth, if the depends upon the resistance value, we can get the current will be vary. So if the R is very small, we can get the maximum current. If the R is minimum, we can get the medium amount of current. If the R is very high, we can get very low value of the current. Then the relationship between resonance, bandwidth, selectivity, and quality factor for a series resonance circuit begin defined. Resonance frequency FR equal to XL equal to XC, that is omega L minus 1 by omega RC, that is equal to 0. So omega R square equal to 1 by LC. Therefore omega R equal to 1 divided by root of LC. What about the relationship between current? The Imax, that is equal to maximum voltage divided by R square plus omega RL minus 1 by omega RC the whole square. For lower cutoff frequency, so we can have two frequency, that is half frequency, that is P maximum power divided by 2. For Im divided by root 2, we can get the max half of the power, so 0.707 Im. So upper cutoff frequency omega h, that is equal to R divided by 2L plus root of R plus 2L the whole square plus 1 by LC. That is an upper cutoff frequency. So bandwidth, that is the difference between higher cutoff frequency minus lower cutoff frequency, that is called bandwidth. Quality factor Q equal to omega R L divided by R, or otherwise it is XL by R, or this XC by R, or another we can represent 1 by R root of LC. That is all we can. These are all the equations for quality factor Q. We can represent the quality factor XL by R or XC by R, or 1 by R root of L by C. Hope you can get what is the resonance, what is series resonance circuit, and what is the application of series resonance circuit, and what is the current, and what is the lagging leading combinations of the resistance circuit, and all we can discuss in series RLC circuit in this lecture. Upcoming lecture we can solve the problems in series RLC circuit. Until then, thank you.